Greetings! Welcome to Electronics 2. This is lecture number 31 and I am Razavi. Today we will continue to look at negative feedback circuits, and our objective is to reach a point where we can analyze various feedback circuit topologies. But before we go there, we still need to build some foundation, and to get there we will today talk about types of amplifiers. Something that we haven't quite seen in the past, but is necessary for understanding feedback circuits. And then talk about sense and return mechanisms. We briefly looked at what we mean by sensing a signal and returning or subtracting a signal in a feedback circuit. But now we want to understand that more clearly, especially at the circuit level. All right. But first, let's briefly look at what we covered in the previous lecture. We went over properties of feedback. So we said that in a negative feedback system like this, we benefit from the fact that the closed loop gain is only a weak function of the open loop gain, because it's approximately equal to 1 over k if the loop gain is much greater than 1. And because of that, we saw that we have what we call gain desensitization, meaning that this gain is not very sensitive to variations in A1. We also saw bandwidth extension, meaning that the closed loop bandwidth of the circuit tends to be greater than the bandwidth of the original circuit that we had bought and we had built. All right. And the two other benefits were, number one, the input and output impedances of the circuit would change after feedback is applied. So those that we see into here and to here will not be the same as those of the original amplifier. And finally, we saw that the linearity improves. The circuit is more linear after we apply negative feedback around it. All right, then we also went back to some very basic concepts from circuit theory, because these are the things that we need as we go deeper into feedback circuits. And we talked about good voltage and current sources, and by that we mean how ideal can a voltage source be. We saw that an ideal voltage source has a zero output resistance. In reality, there is some, and we prefer that to be small. For a current source, ideally, the output impedance is infinite, and again, in actuality, you would like it to be relatively large. So those are attributes that we need to keep in mind as we examine different circuits and see if they are they approximate a voltage source or they approximate a current source. And then we also talked about sensing voltages and currents. So suppose I have a simple common emitter stage and I want to measure the output voltage. So I use a voltmeter here, but the voltmeter must not disturb this voltage, must not change this voltage when it wants to measure it. So That happens if the resistance of this voltmeter is infinite, right? So ideally that should happen. So any circuit that must measure a voltage must have an infinite or a very high input impedance. For current measurement, suppose I am interested in the current flowing through this transistor to ground. I cut this wire and inserted this current meter in series with this wire. Okay. Now again, I don't want the circuit to know that I have inserted an ammeter in series with the emitter. So the resistance of this ammeter should be close to 0 so that we don't degenerate this device. The circuit doesn't feel the existence of the current meter. Okay, so those are again two important principles that we need to know. Any circuit that is supposed to measure a current, sense a current, will go in series, will cut the wire, put it in series, and that circuit must have a very low impedance between these two terminals. All right, today we will begin with types of amplifiers, and we want to categorize these carefully so that when we get to feedback topologies, we don't get confused. So let's talk about types of amplifiers and see what we have here. Now, the type of amplifier that we have seen primarily in Electronics 1 and in this course so far is a voltage in, voltage out amplifier, right? That's what we've been mostly familiar with, and it's intuitive. We apply a voltage to the circuit, it amplifies it, and it gives us a voltage, right? So that's one type. So we will call that a voltage amplifier. So here's a notation for it. So V in, V out, and it has some voltage gain, so we call it AV, voltage gain. All right, so let me draw this V in as a voltage source so that we're clear on that. Okay, and V out is generated between the output and ground. All right, so a common emitter stage is like that, a cascade stage is like that, a common base is like that. All of these are voltage amplifiers. All right, but that need not be the case all the time. For example, the input quantity doesn't have to be a voltage, it can be a current. So I can envision a situation where my input is a current quantity, but my output is still a voltage quantity. All right. So now that looks a little strange, doesn't it? We haven't seen this before. What is the meaning of this? Where does this current come from? And why are we applying a current to an amplifier, not a voltage? Well, there are some applications where this really happens. So again, without going through too much trouble, most of the cameras, in fact, the camera that is capturing my image right now, in its sensor has a current for every pixel, and that current has to flow through an amplifier like this. In optical communications, we have the same situation. So in some applications, not all applications, in some applications, maybe 20% of applications, we have a current quantity representing the signal of interest. And that current has to flow through some sort of amplifier and eventually give us a voltage. We would like to have a voltage because processing this voltage is easier, right? So what do we call this circuit? We call this a voltage amplifier, right? Voltage to voltage. But here we have current to voltage. So this has a name. This is called a trans impedance amplifier. Okay, just the name, trans impedance. So a trans impedance amplifier measures a current, senses the current, amplifies the result, and gives us the final output in the form of a voltage. All right, so that's okay. We will see some examples of the implementation of the circuit, so don't worry about that. But how do I define a gain for the circuit? Here it was easy. We set the output amplitude divided by the input amplitude would be the voltage gain. But then here we have two different dimensions for the input and output. So that's okay. We will still take the output amplitude divided by the input amplitude. So we're dividing voltage by current, right? So the gain is output voltage, the small signal voltage, divided by the small signal current. That's what we call the gain of the circuit. So what should I call this? What's the unit? The unit is resistance, right? So in fact, I'm going to call this R0. R0 is the gain of the circuit. And the unit is ohm, right? Ohms. Very strange, right? So, but it's not really that strange. If you think about it, all this means is that, for example, if R0 is 1 kilo ohm, so R0 is 1 kilo ohm, it means that if the input current changes by 1 milliamp, okay, if the current changes by 1 milliamp times 1 kilo ohm, the output voltage changes by 1 volt. That's all. So we apply the, let's say, 1 milliamp of positive current, the output voltage changed by plus 1 volt, and vice versa. That's what it really means. So this is the way we quantify the gain of this type of circuit. Okay, so now you see where I'm going, right? We had voltage, then we had current voltage. What else? We have two other possibilities, right? Okay, so the other possibility would be that we have an amplifier and it takes a voltage from us, but it generates a current at the output. Okay, so we have a current at the output, a small signal current in response to a small signal voltage at the input. All right, so what should I call the circuit? The circuit also has a name. We will call this a transconductance amplifier. See, this was transimpedance, transresistance, if you will, right? Impedance. This will be transconductance. So this is called a transconductance amp. And the voltage gain, the gain is defined as the small signal output divided by the small signal input. So I out over V in. What's the unit? The unit is 1 over ohm, right? So we will call this GM. So the unit is 1 over ohm, and the gain of the circuit will be denoted by GM. This is familiar, right? We defined the transconductance of a circuit before. Now, at that time, we weren't thinking the output should be voltage or current or whatever, but in the transconductance test, we did look at the output current of the circuit, right? So yes, so this is like that, except that this output may generally be just a current. It never becomes a voltage, right? So V in goes to the input, and the output current is I out. The gain is denoted by GM. So again, we might say that the gain of the circuit is 1/1000th of divided by ohm, right? 1/1000th of 1 milli. So this 1 over ohm also has another name, which we call Siemens, like the company. So we might say that the gain of the circuit is 1 millisiemens. And what that means is that in response to a 1 volt change at the input, the output current changes by 1 milliampere. All right? Okay. And lastly, we can have a current going to the input and a current coming from the output. So that would be something like this. We have I in going in and a current flowing from the output node. This is just called the current amplifier. This is called the voltage amplifier. This is called the current amplifier. And the gain is denoted by AI. AI is defined as I out over I in. So these are a little simpler to understand because the dimension doesn't change. We have a voltage at the input, voltage at the output, or current at the input, current at the output. But these two are a little less familiar, less intuitive, because we have current at one port and voltage at another port. All right. Okay, so at this point, these look rather abstract, but I can quickly show you some examples of the circuits that we've seen in the past that can fall into these categories. Okay, so let me just use a different color and sketch a few very simple circuits on top of these to show you. All right, so voltage amplifier, that's easy. We've seen this a number of times. So here's an example of a voltage amplifier. Okay, a common emitter stage. All right, how about this one? This circuit takes a current and gives us a voltage. Can you think of anything that does that? A circuit takes a current and gives us a voltage. Can you think of a device that takes a current and gives us a voltage? Sure, a resistor, right? So this could be just a resistor. It wouldn't be very useful, but it could be a resistor. So this could be just a resistor to ground, right? So this whole thing is a resistor. The current flows through the resistor, gives us a voltage, and that the gain of the circuit would be just this resistor value. But can I make something more interesting, maybe more useful than this? Sure, I can connect this to a common emitter or common source stage and then declare this as the output voltage. Do you agree that this circuit is this? We have a current. We allow the current to flow through a resistor. Again, this is all small signal, right? We allow the current to flow through a resistor. That generates a voltage. That voltage gets amplified and comes out and becomes a bigger voltage. So that's V out. So this whole circuit qualifies as a transimpedance amplifier because it takes a current and converts that current to voltage as it goes through. All right, how about this circuit? This circuit senses a voltage and gives us a current. Do you know of any device that can sense a voltage and give us a current? Sure, transistors, right? They do that all the time. So here's a simple implementation. We have V in, and then we have I out. That's a simple implementation of a transconductance amplifier, right? We see that we give a voltage to the gate, the transistor converts that gate source voltage to a current, and that satisfies this picture of a transconductance amplifier. Okay, and finally, this one, it takes a current and gives us a current. Do we know of any device that can do that? Well, maybe a transistor. So here's a transistor. A bipolar transistor maybe. So if we give a current to a bipolar transistor, the base, it multiplies that current by a factor of beta, right? It has a current gain of beta. So this would be I out and would be beta times I in. So that's a current amplifier, right? So that's another example. So we see that, in fact, this abstraction, this model that we have created for these amplifiers may just represent parts of the circuits that we've seen in the past. Or from another perspective, if I am given a really complex circuit, in my mind, I can try to break it into pieces like these. And that greatly helps me analyze the circuit and try to quantify its performance. All right, so these are the 4 types of amplifiers that we will need when we get to feedback systems. But I need to talk about a couple of things. So, input and output impedances of 4 amplifier topologies. All right, so I am building these amplifiers, right? A voltage amplifier or a transimpedance amplifier and so on. And what I'm asking myself is, how should I choose the input impedance and the output impedance of this amplifier that I'm building? Ideally, what should it be? And in practice, how close can I come to that ideal situation? All right, okay, so let's draw those again. And we go back to this picture here. Okay, that picture helps us understand what we should do. All right, so here's a voltage amplifier. So I'll just say AV so that we know it's a voltage amplifier. What should the input impedance of a voltage amplifier be in the ideal case? Well, the purpose of this circuit is to sense a voltage. And when we sense a voltage, we don't want to disturb the preceding circuit. Just the way this voltmeter must not disturb the preceding circuit. So ideally, the input impedance of the circuit is infinite. All right, so that means the input impedance, right? Okay, now, how about the output impedance? So let me clean this up a little bit so that it's all organized. So R in is equal to infinity. How about R out? All right, this circuit produces a voltage. So it wants to act as a voltage source, right? It wants to deliver a voltage. So what is a good voltage source? A good voltage source, according to our study last time, is one that has a very low output impedance, right? So the output impedance of the circuit has to be ideally zero. Okay, in practice, of course, it won't be, but ideally it should be like that. All right. So that's the model that we have for a circuit that senses a voltage and generates a voltage. In the ideal case, it interfaces very easily with the outside world. It interfaces on this side with the preceding circuit easily because it doesn't load the preceding circuit. And in this case, it interfaces with another circuit, with another load very easily because it can drive any load. Even if the load is 10 ohms or 1 ohm or 5 ohms, it can still drive it because the output resistance is very small. You can think of this as a Thevenin equivalent resistance for this circuit. All right, so now let's move on to the next topology and see what you should expect here for the transimpedance amplifier. All right, so here's what we have. So we have a current going in, I in, a voltage coming out, and this is what we call a transimpedance amplifier. So what should the input impedance of the circuit be in the ideal case? In the ideal case, R in. All right, so remember, we're trying to measure a current somewhere in some system. And when we want to measure the current, there's a current through some wire somewhere, right? And we want to cut that wire and put this guy in there to measure that current. That's this job. So this guy must not disturb that circuit, just the way this current meter must not disturb the circuit. So the input resistance of the circuit must be zero, so that when we connect it to that preceding stage, that stage doesn't feel it. So this should be zero. I know this is very unintuitive, right? Unlike this is difficult to understand. But as we go along and we look at examples, you will see. All right, how about the output resistance or output impedance? Well, that's similar to before because here we also have an output voltage. We're trying to deliver a voltage, so we want to be a good voltage source. So then this should be zero. All right. Okay, so now very quickly we can see what it happens for how it happens for the other two, right? Because these are just extensions of these. So if we have a transconductance amplifier, sometimes we call this just a GM stage, then because we are sensing a voltage this should be infinite because we are delivering a current. This should be what? If you want to deliver a current, you want to act as a good current source, right? If you want to act as a good current source, what should it be like? The output impedance should be infinite. So this output impedance should be infinite. And then finally, in the case of a current amplifier, I in and I out with the gain of AI, we have infinite here, sorry, 0 here because we're trying to measure a current, and we also have infinite here, and then because we are delivering a current, oh sorry, I made a mistake again. Let's see here. Because we are trying to measure a current, the input impedance should be 0, and because we are trying to deliver a current, we want to act as a good current source, the output impedance should be infinity. All right, so that's the picture that you need to keep in mind for these 4 amplifiers. Okay, ideally we want to be like this, but in practice, of course, it won't be like that. All right. So let's look at some more examples of amplifier implementations, just so that all of these are reinforced in our mind. So examples of amplifier implementations. I showed you some very simple examples earlier, right? These little black circuits that I drew here. So I want to now to go one step further and see what I can do to build amplifiers that approach these ideal situations. Okay, so for voltage amplification, I would like to have a very high input impedance. So what kind of topology and what kind of transistor should I use? Well, a common gate or common base is no good because the input impedance is low. So I should go with a common source or common emitter stage. If I use a common emitter stage, the input impedance is R pi. It's not that high. So I should use a common source transistor. So here's a common source transistor that senses a voltage, and its input impedance is very high, right? So I'll just say very high. So that's a very good mechanism for sensing a voltage, right? We are sensing it just like this voltmeter with a high impedance. Okay, but the output impedance is not that low, right? This is RD. I was looking for a very low output impedance, but this is like some kilo ohms or hundreds of ohms. So what do? Well, I can follow this by a stage that has a low output impedance. What kind of stage do we know from Electronics1 that has a low output impedance? Followers, right? Emitter followers, source followers. So let's use something here. I can use maybe an emitter follower, right? So now we see that this is a low impedance, right? So we say low. Not very low, but pretty low. Okay, so this is an approximation of this voltage amplifier. It has some voltage gain, which we can calculate from here to here, and it has a high input impedance, and it has a relatively low output impedance. All right, let's look at the transimpedance amplifier. So I said that to build a transimpedance amplifier, we can do something like this, right? So let's go ahead and do that. We have a current. The current has to flow through something, right? The current, you cannot see infinite impedance, preferably a low impedance. So do I know a circuit whose input impedance is low? Sure, common gate, common base topologies are like that. So let's use a common base topology that has a low input impedance, right? This is 1 over GM if we neglect the early effect. So For example, if the bias current is 1 milliamp, 1 over GM is 26 ohms. That's great, right? Okay, and then we have a resistor here in the common base stage. But again, this resistor is not that small. I am looking for a low output resistance. So just like here, I am going to follow it by some sort of emitter follower or source follower. So here's an example of emitter follower or source follower. So this has a low input impedance, and this is also low input impedance. So we are coming close to that ideal model. This is a transimpedance amplifier. All right, how about the transconductance amplifier? Well, we said that a single MOS transistor can do the job. So here's a single MOS transistor sensing a voltage. We are trying to sense a voltage with a high input impedance. That's great, we can do that. But then this output impedance is not that high, right? This is RO. Can I make it higher? Sure, I can make it cascade, right? So I put a cascade on top of this, VB, and now this becomes a pretty good transconductance amplifier, right? We have a relatively high impedance here, very high. And we also have a high impedance looking out here, very high. So we are approaching this picture. We have some transconductance. The transconductance of the circuit, which is defined as I out over V in, is approximately that of this device, if you remember from our studies of cascade structures before. So we have gain, and then we have a high input impedance, we have a high output impedance, so that's a nice implementation of a transconductance amplifier. And lastly, we are looking for a current amplifier. So how can we do that? Well, here's an example. We want to have a low input impedance, right? So why don't we use one of these guys here? And here's a low input impedance. So we say low. And then I want to have a high output impedance. This impedance is not that high, right? It's just RC. So what can I do? I can try to cascade it. So let me just do that. I will, let's see if I go here and I erase this resistor. And I will instead use a cascade structure. So here's a cascade structure. So we'll call this VB1. VB2, and this is a high output impedance, right? Okay, so you see that these circuits are a combination of techniques that we have learned in the past with the idea of trying to have a high input impedance or low, and high output impedance, low output impedance or high. Like in this case or in this case, right? So depending on what we're trying to do, we can use, for example, followers to create a low output impedance, or cascades to create a high output impedance, and so on. All right, so these are some simple examples of that. So we haven't got to feedback circuits yet, okay? This is just the basic stuff that we need, because later on we're going to take these and apply feedback around them and so forth. But all of these have to be crystal clear in our mind so that we can analyze feedback circuits without confusion. All right, let's go to another page, and I need to talk about the models of these four amplifiers. So let's go and do that. So, models of four amplifier topologies. We haven't talked much about modeling amplifiers in Electronics 1 and Electronics 2, but here we really need that. The situation is that when we get to a complex feedback circuit, we have to have the proper model of each block in our mind. Otherwise, we can really get confused or just not reach a nice and intuitive result. So what we mean by model here is that I am given, for example, a voltage amplifier. So V in, V out, with a gain of AV. Okay? This is a black box. How do I model this using basic circuit elements, voltage sources, resistors, current sources, that sort of thing? Okay? So that when I want to analyze, I can quickly write KVLs and KCLs. All right, well, what should this look like? We know that this circuit generates a voltage at the output equal to AV times V in. So that would be a dependent voltage source equal to AV times V in. And where is V in? Well, V in is just the voltage that appears here. So do you agree that this is a model of that? All right. How much is the input impedance here? It's infinity, right? It's an open circuit. So that's good because that's what we wanted. So looking into here, we have infinite. And looking into here, how much do we have? It's an ideal voltage source, so we have 0. So if this is an ideal voltage amplifier, this is the model of that ideal voltage amplifier. All right. But let's say that you built an amplifier and it's not quite ideal. So what if the amplifier has an input resistance? How do I model that? So let's draw this again. This is for the ideal case. For the actual case, we need to have an input resistance. So we're going to draw it like this. And we call this one R in. And V in is applied here. That's V in. And then the voltage, dependent voltage source is here, AV in. And that's the output. So this circuit has an input resistance of R in. You can see that if I apply Vx and I measure Ix, I see R in. So that is the input resistance of the circuit. If the input resistance is 10 kilo ohms, I can pick this to be 10 kilo ohms. All right, but what if the output resistance of the circuit is not 0? Right? In the ideal case it is, but in reality it's not. Let's say it's the output resistance of a source follower. 550 ohms, 100 ohms, right? What do I do? So now I have a voltage source, but that voltage source is not ideal. How do I make it non-ideal? Remember what I showed you on the previous slide? We said, well, we have to model it by a resistance here, which we call R out. So this is the model of an actual voltage amplifier, right? This is in the model of an ideal voltage amplifier. Okay, so then let's do this. We'll make a table here. And I will add some notation here. So this is the ideal model. This is the actual model. All right. So if you have an ideal voltage amplifier, that's the model. If you have an actual voltage amplifier, that's the model. All right, so we have to repeat this effort for the other 3 types of amplifiers as well. So no problem, let's go to the transimpedance amplifier. So here we have I in, the gain is R0, we have V out, right? So we said that ideally the input impedance has to be 0 because we're trying to sense a current, we're trying to measure a current without disturbing the previous circuit. So that would be like this. It would be a short circuit to ground, I in, and then the output is the voltage source. So, and the gain is R0, so this would be R0 times I in. This is very strange, isn't it? It's very strange, and I have a wire here just going to ground, and then what this voltage source does is it looks at the current through that wire, somehow magically, and then generates a voltage equal to that current through that wire times R0. Okay, but it's just a model. That's the only model we can build, because the input impedance has to be 0. Remember, ideally for a current sensing circuit, and the output impedance has to be 0. So that's what we get. There's no other way. Okay, how about the actual model? Well, in the actual circuit, the input resistance will not be 0, it will be some amount. So how do I model that? That would be I in is coming in, and we see this resistance, which we call R in. Okay, and then the output is a voltage source with a finite output impedance, just like what we saw for the voltage amplifier. So here's the voltage source of R0 I in, but then we also have a resistance of R out. So this part of circuit is similar to this one, right? Because we're generating voltage with a finite output impedance, but this part of circuit has an input resistance through which the current must flow. Okay, all right. We have 2 more amplifiers to go. So let's do that. The next amplifier is a transconductance amplifier. It senses a voltage, gives us a current, and the gain is denoted by GM. All right, so ideally, we are sensing a voltage, so we have an infinite input impedance. We are generating a current, so we have a current of I out, which is equal to how much? I out is equal to, according to the gain equation, is equal to GM times V in, and V in is just here. So the input impedance is infinite because we are sensing a voltage. The output impedance is infinite because we are delivering a current. We're acting like a good current source. So this is also infinite. Okay? And lastly, we have to find the non-ideal situation. Non-ideal situation is, again, the input impedance is finite. So here's R in. And the output impedance is also finite. But remember, for a current source, the output impedance becomes parallel to the current source because we're building a Norton equivalent, right? So that's R out. And this is still GM times V in. And V in goes here or between these 2 terminals. So that's the model of a non-ideal transconductance amplifier. Okay, so for the 4th type, it should be straightforward, right? So this one has a current at the input and a current at the output. So ideally, we want to sense a current without affecting anything. So we need a short circuit. We need a 0 impedance here, I in. And then we are generating a current at the output. So this is a current with some factor, AI, I in. It's just a current-controlled current source, current-dependent current source, right? The gain is AI. And again, in the non-ideal case, the input impedance will not be 0. So there is some finite resistance here. And then the output impedance will not be infinity. So there is a finite impedance here. Okay, so these are all the models that we have for these 4 amplifiers. All right, so it's important to remember these, and again, anytime you don't remember, just go back and check this table, and we just have to go back to the fundamentals, sensing a voltage, sensing a current, what impedance does that require, generating a voltage, generating a current, what kind of output impedance does that require, right? Based on those, you can always find these models. All right, the last topic that we need to talk about today is the sense and return mechanisms. I don't have time to do that, but I'll just briefly give an introduction, and next time we'll pick up from here. So we want to talk about sense and return mechanism. So let me just explain what this is all about, and then next time we'll elaborate. So here's our feedback system. X and Y, A1 and K. So sense mechanism means, how do we sense here? So how do we sense? And by this how, we really mean what kind of circuit should go here. By now you might guess that we can have one of 2 quantities at this point, a voltage or a current. So how do we sense a voltage? How do we sense a current? And similarly, this is called return mechanism here. So how do we return a voltage or a current? Meaning, how do we subtract or add 2 voltages or 2 currents? Exactly what kind of implementation would this require? What do we expect of this guy to be able to perform that returning action, to return the voltage or the current? And so we will see that we, based on what we have learned so far, we have some idealized model for this feedback network so that we can sense a voltage or a current, or we can return a voltage or a current. And those are interesting details that we will come back to next time. I will see you next time.